Okay, first we talked about the common logarithms. We've talked about the change of base formula. We've talked about natural logarithms. We've done a little bit with figuring the integrals and derivatives. Today I want to go through, and we talked the other day about the growth and decay, exponential growth and decay, and I gave you a formula the other day in the notes. We went through this formula, okay, where the y represents the final amount. The y sub 0 stands for the initial amount that you start with. It might be like growth of bacteria was 1. We did an example the other day with a half-life of a radioactive element. But that's kind of the main formula. And I want to go through an example. I saw this, it's been quite a while ago, and it was a sponsor, a PROM sponsor out in Van Nuys, California, and he was also a math teacher. And he had been the PROM sponsor since 1961. And instead of like here where you sell magazines and you work to earn the money to go to PROM, they would just pay to get in the door. Pay so much per couple to get in the door. And what he noticed was the price kept going up and up and up. And what he wanted to know was it growing exponentially? There's a difference between, if you say something's growing like linearly, the cost might be going up like that. But if it's going up exponentially, it's going up like that, okay? So, and he had all the data since he was the sponsor, okay? So, basically, I want to take you through this PROM problem. And he wants to know, I'm not giving you the exact, he just wants to know, was the cost of PROM going up exponentially? Okay, so what he did was he went back and looked at the real data that he had. And Van Nuys, California is a rich area, okay, very affluent, okay. So the real data that he had was back in 1961, it cost $4 a couple to get in the door, okay. In 1989, okay, it cost $87 a couple to get in the door. So that was quite a jump, and it had been going up and up and up. So he wanted to know, was it going up exponentially? Okay, so he looked at the data and used the formula y equals y sub 0 e to the kt power. And he said, okay, the final was $87. The starting was $4. And E, the K we don't know. And if you figure the difference in years here, there were 28 years. Okay, so what he's figuring now is what's the K? What's the growth constant? Okay, so first thing he did was he divided by 4. Okay, and if you do that, you get 21.75 equals E to the, I'm going to put the 28 in front, 28K power. And then we learned the other day that if you figure the natural log of the 21.75, there's more than one way to work this problem. We went through it the other day. One way is to take the natural log of that, and basically if you take the natural log of both sides, okay, if you're in the exponential form, you can solve it by going to logarithmic form. And the natural log of 21.75 is 3.0796. You agree with that? Third law of logarithms. Third law of logarithms says this goes out front. So you'd have 28K times the natural log of E. Well, this natural log of E natural log of E, it's understood to be a base E. So what you're really saying is E to what power equals E to the first? 1, right? So this is equal to 1. Okay? So you're saying 3.0796 equals 28K times 1. So just 28K. So divide by 28. So divide by 28. Okay, and I get you agree with that? And that's your K value. You okay with that? Everybody okay with this part? You're just saying E to what power equals E to the first. It's got to be 1. E to the first equals E to the first. Okay, so then what he did was he tested it and said, okay, test it. Go back, because he had all the data. He said, test it for 1979. Okay, so you go back to the same formula, y equals y sub 0, e to the kt power. The y, we're going to figure out what the equation says it should be, and then he has the actual figure. Okay, so we still started at 4. Okay, the e, now we know the k is 0.1100, and from 1961 to 79, we got 18 years. Okay? Okay, so figure. We could take this times 18, what we got on the calculator, right? And then take e to that power. Remember, e is right above the ln. So e to that power. I get 7.24. There's more than one way to work this too. We got 4 times 7.2409. Okay, so take this times 4. Okay, and y equals 28.96. $28.96. Then he went back and looked. It was a little off. Okay, the y, the actual, I guess I shouldn't call it y. The actual was $30. Okay, but basically it was real close to going up exponentially. Now, if that's the case, okay, what would it have cost you to go to prom in Van Nuys, California this year? Okay, so now you got to figure that. Okay, so we got another. So y equals y sub 0 e to the kt power. We don't know the y sub 0 was 4. The k is still the 0.1100, and that's rounded. And we're going 2013 to, what was it, 1961? Okay. 52 years? Okay. Okay, so if we take the, and we're rounding that because I didn't store that. I should have stored that value. Okay. Times 52. And then e to that power. And then take it times 4. How much did you guys have to earn to go to prom this year? 70, 75? Yeah. That's looking pretty cheap right now. Okay. If it continued to go up exponentially, it would have cost you, $1,219.62. Okay, now let's make this a little bit more interesting. Let's extend this out. Okay, so let's give you guys, let's give you like 5 years, so 2018. Okay, and then let's say you have a kid. Okay, so we got 2018, and then we got probably 18 more years. What's it going to cost you to send your kid to prom Okay?
Kid's not going to prom.
Kid is not going. Okay, so let's go another. Y equals y sub 0 e to the kt power. If it continued at that growth rate, still started at $4, e, k is still our growth. Oh, wow. How many years have we got? 75 years later. Ooh, okay, so 0.1100 times 75. And then take it times 4. You might want to start saving. You agree with that? Is that what you got? Yeah. Which one do you want? $15,310.50. Now, this is why sometimes people have got to say, okay, this is getting out of control. If things are growing exponentially like that, you got to say, wait just a minute. Somewhere we got to draw the line. That started happening here, and I was concerned about that with project graduation. This would have been just in the first 5 years that it started. Okay, you know, all of a sudden parents were trying to beat other parents, and we're going to raise more money and all that, and then it's like, whoa, wait a minute. If you start doing that, you know, at a certain point, you're not going to be able to afford it. Okay, you got to start thinking about things in your lifetime right now. Okay. And what's going up exponentially? Okay, I would like to be able to go back in my lifetime and look at the price of Coca-Cola. Okay, look at the price of like Coca-Cola. The size that I had for lunch right now, I used to pay a nickel. Okay, now how much is it? You know, has it gone up exponentially? Has it gone up? And things can still go up. They can be linear growth. It doesn't have to be exponential. But, you know, I always give the example of 6 hamburgers for $1, you know. Has it gone up exponentially?
Now it's one burger.
Yeah. You know, so you got to think in your lifetime what might have gone up exponentially. Gasoline, you know, and it would be interesting to plot it to say, is it a linear growth? Could be a line of best fit, and you can do the statistics on it and figure out how is it growing. But there's exponential growth and exponential decay. A lot of you are interested in, like, you know, and I had some last year interested in forensic science. But forensic science, you're basically doing the same thing, but you're looking at exponential decay. You know, if they find a body somewhere and it's, you know, and they say that body's been there for 10 years or, you know, 50 years or 100 years, how do they know? Because they know the half-life of carbon, okay, and our bodies are made up a lot of carbon. So anyway, that PROM problem, and this guy was the actual sponsor, so I thought it was kind of interesting, you know, to look at that problem. Okay, makes you think about it. So as parents down the road, you know, if you have to put squelch on something, don't feel bad about it. You're saving people thousands of dollars down the road. Okay? Okay. That was just one problem I wanted to look at. You can draw a little separator there. We're going to add, and I'm covering a little bit of everything in this. If you look, you know, in this book, they cover a bunch in one section. So we have different integral formulas on your card already. We have formulas on there for like sine and cosine. Today we're going to get the integrals of tangent and cotangent of x. Tangent of x and cotangent of x. Okay, so we're going to look at the integrals of tangent of x and cotangent of x. Okay? First, if you look at the integral of tangent of x with respect to x, do you remember from trig what's tangent in terms of sine and cosine? Sine over cosine. Okay, so you can write it as sine over cosine with respect to x. Okay, that's just using the trig. Tangent is sine over cosine. Now we're going to use the integration by substitution. Let u equal the cosine of x. Then du, what's the derivative of cosine? Negative sine of x with respect to x. Now, you can substitute for cosine, we can substitute in the u, okay? And then we need to get rid of this negative, okay? Because we need to be able to sub in for sine of x dx. So, multiply by -1 on both sides. Okay, and remember when you're doing this part over here, you're working with the derivatives. Okay? Okay, so if we rewrite this, we end up with the integral of 1 over u, and then it's a negative du, but I would go ahead and put that negative out front. Okay? And then from what we did last week, okay, the integral of 1 over u with respect to u, if you look on your card, I think we added this to the card, it's the natural log of the absolute value of u. And then since it's an indefinite, we have to put that plus c. But then what was u? U was the cosine of x. So it's a negative natural log of the cosine of x, the absolute value of that, plus c. With this -1, if you work the third law of logarithms backwards, this -1 is actually going to go back up here. Okay, so that's the natural log of cosine of x to the -1 power plus c. But cosine to the -1 power, what's that negative exponent do? Moves it down. Okay, so that's going to be the natural log of 1 over the cosine of x, and then plus c. But 1 over the cosine is, cosine's a reciprocal with what? Secant. Remember, the c's don't go together. Okay? So, here's the final formula. The integral of tangent of x with respect to x is the natural log of the secant of x plus c. Okay? So, we're going to add that to the card. Now, I kind of just went through the proof of that. On cotangent, we're not going to go through the whole thing. It's cotangent of x with respect to x equals the natural log of the absolute value of sine of x plus c. Okay, so add both those formulas to your card. Okay, then draw another little separator. Last week we did a logarithmic differentiation problem. Today I'm going to go through another example. Okay, refresh your memory a little bit. Use logarithmic differentiation to solve. Okay, and the problem is y equals x to the sine x power. X has to be greater than 0. And basically, when they're saying use logarithmic differentiation, they're asking you to find the first derivative And remember, when you get done with this, when you found the first derivative, what you've actually found is the slope of the tangent line to that curve. Okay? Okay. To solve by logarithmic differentiation, first step, take the log of both sides, and we're going to do natural log. Okay, so natural log of y equals the natural log. And the reason you do this is because you have a variable up here as an exponent. Anytime you got a variable up as an exponent, you've got to use logarithms to solve. Okay, so you have the natural log of x to the sine x power. Okay, and make a note out here at the side. What did we do on this step? You just take the natural log of both sides. Basically, all you do is write ln on both sides. Okay, and then third law of logarithms. Third law of logarithms, this goes out front. Okay? So it's the natural log of y equals sine x times the natural log of x. Okay, so this would be apply the third law of logarithms. Now, it's been a while. This is the critical part right here. Sine x times the natural log of x. And you want to find the derivative. What rule? Times product rule. Product rule. Okay? So, on this one, and on the left side, when we're figuring the derivative, we did this in the first problem also. When you're figuring the derivative, you actually have to use implicit differentiation. Derivative of natural log of y is 1 over y, and then times that extra dy over dx. Remember, the one thing we did last week was if we said if y was natural log of x, the derivative y prime is 1 over x times the derivative of x times 1. Remember that? Okay, so on this side, now, product rule. Product rule says leave the first one the same. So that's the sine x. Times, what's the derivative of the natural log of x? 1 over x. Product rule, you leave the first one the same, times the derivative of the second, then what? Plus. Then you leave the second one the same, times the derivative of the first. So you have to say, what's the derivative of sine x? Cosine x. Okay? Okay so far? Okay. We can multiply, we want to get this by itself, so multiply by y on both sides. So we'd have the derivative of y with respect to x equals. We're going to put that y in front. And I'm going to rewrite this as sine x over x plus the natural log of x times the cosine of x. Okay, so all I did was rewrite, put the sine x on top and the x on the bottom, and I multiplied by y. So I left out something up here. We need product rule. And take the derivative of both sides using implicit. That's when you have to take the derivative of a y term, you have that extra on the left side. And product rules on the right side. Okay? And then I just multiplied by y on both sides. Multiply by y on both sides. Okay, and then if you remember, what's y? So you got to go back up here. Y is equal to this. So you got to sub that in right here. So the derivative of y with respect to x is x to the sine x power, and then sine x over x plus the natural log of x times the cosine of x. So all we did there was say, what is y? It's back in the original problem. So sub in for y from the original problem. So you found the derivative of x to the sine x power, okay, using logarithmic differentiation. Okay, that whole thing is your answer. Okay, this whole thing, if they gave you an x value and you wanted the derivative of that original, you sub it into that, and you'd actually be finding the slope of the tangent line to that original curve. Okay. Okay, so that's your second example with logarithmic differentiation. Okay, draw another little separator. Okay, I'm going to go through a few more equations, and we're going to add a couple of these to the card. These are equations involving the natural log of x, and e to the x power. Remember, they are inverses of each other. We did that in the notes earlier. They're inverses of each other. If you graph them, they're symmetric with respect to the line y equals x. Okay? What if I give you y equals e to the x power? Okay? Okay, you're in exponential form. Okay, if you go to logarithmic form, okay, the natural log of y, the base is e, and it equals x. Okay, that's exponential form. This one is exponential. It's just like we did earlier. We did something like this. If I said 2 to the third power equals 8, that's exponential. If I wrote it in logarithmic form, I'd write the log of 8 base 2 equals 3. Doing the same thing here. This is the logarithmic form. Okay. E is the base, x is the exponent for the logarithm, okay, and y is the number. Okay. Most of the time, they won't write down the e. They'll just say the natural log of y equals x. So this is exponential. This is logarithmic. Okay, they are inverses of each other. Okay. If I had another equation over here, let's say I have y equals the natural log of x. What's the base in that? What's it understood to be if it's natural log? E. E to what power? Remember, a logarithm is just an exponent. E to the y power equals x. So this is logarithmic form. This is exponential form. Should be able to go back and forth. Okay. Now that's just going back and forth from the two forms. Okay. Another equation that they give you in this section is the natural log of e to the x. Okay. Now, if you look at this, what's understood to be the base down here? It's understood to be a little e down here. E to what power equals e to the x? E to what power equals e to the x? X. Okay? Because this is understood to be a little e here. E to the, basically you're saying e to the x power equals e to the x. Yeah. Okay? And that's for all x's. Okay? Another one, e to the natural log of x power, e to the natural log of x power, I didn't write that very good, e to the natural log of x power equals x for x greater than 0. So like if I said e to the natural log of 9 power, what's it equal? Just 9. Just 9. Don't make those hard. Okay? Okay, there are two formulas there that I want on your card. Those two. Take a minute and add those to the card. Okay, go back to this one a minute. If I just said natural log of, e to the 7th power, what's that equal? 7. Okay? Don't make those hard. Okay? Okay, I want to go through two examples, then I'm going to give you time to work. Okay? Say they ask you in the homework to solve for y. Let's say they give you the natural log of y equals 3t plus 5. Okay? That's in logarithmic form. What's understood to be the little base here? E. So it's e to what power? Yeah, to the 3t plus 5 equals y. Okay? And that's as far as you go. I didn't give you a t value. So basically you're going from logarithmic form to exponential form. Okay? And a lot of these, that's all they're asking you to do to simplify. Say they give you e to the 2y power equals 10. Okay, anytime you have a variable up as an exponent, to solve it, take the log of both sides. And since it's an e, it's a natural log. So you just write natural log on both sides. Okay. Can you use the formulas up above to simplify the left side? What's that left side go to? E to what power equals e to the 2y? Does that look? E to what power equals e to the 2y? 2y. 2y. Okay, equals the natural log of 10. Okay? Divide by 2 or multiply by. This is probably easier for you to understand if I multiply by a half. If I multiply by a half, it's going to look like this. Okay? And you're going to get y equals. Third law of logarithms. This goes back up here. Okay? So it's the natural log of 10 to the half power. What's anything to the half power? Square root. So y equals the natural log of the square root of 10. Now I could have done that same thing. Let's say I start with this 2y equals the natural log of 10. I could divide by 2, divide by 2. What you cannot do is say that that's 10 divided by 2 is 5. That's not true. Okay? You can say 1/2 natural log of 10. Because that's a natural log in there. Okay? You could do it Now, that's better than going this way. Okay, I won't confuse you anymore. Okay, now, you have 2 different assignments. Okay, if you've been gone umpteen days, and people, I know it's tempting, but it is not over till it's over. Okay, and you're not done yet.